All right, I should have lecture 47 notes, hypothesis testing for difference of means with paired samples. All right, so let me just read what I have here to get us started. We know that hypothesis testing is often used to try to discern whether there has been or will be a change in a population mean because of some intervention or other change. A classic example of this, what we're going to look at now, is a before and after scenario, where we measure a quantity for each individual in a group before and again after an intervention, and we take the difference for each individual. If we did this for the totality of all individuals, the result would be a population of differences whose mean might be 0, which would mean that the intervention made no change before and after the mean was the same, or it might be non-zero, so that the intervention made some kind of a change. Okay, so what we'll do, of course, is we'll take a sample and we'll compute the set of individual differences for a sample and do a hypothesis test for the sample mean to try to determine whether the intervention caused a change. This will make more sense when we do an example, which we'll do in just a second, but let me just summarize that. In bold, the key here is that we take the difference before and after for each individual that we're testing. And so our data set is a set of differences, all right? Everything else on our hypothesis testing goes through as before. Once we get that set of differences, we just proceed as before. All right, so for example, we wish to test the effectiveness of a diet for weight loss. So this is how can you get more classic than before and after? Before the diet, so-and-so weighed this much. After the diet, they weighed this much. All right, we want to test the effectiveness of a diet for weight loss. We recruit 9 individuals who agree to go on this diet for a prescribed length of time. We're saying just 6 months here. We record their weights at the beginning and at the end of the diet. The results are tabulated in the table below. So the before is, here's my weight, after the diet is the after, right? Okay, so if you look, I have a table here where I have the subject, the individual, A, B, C, D, all the way up through I. And so the first person, they weighed 188 pounds before, and they weighed 182 pounds after being on the diet for 6 months. All right, so their difference then is, look what I did. I did after minus before, right? So I did 182 minus 188 and got -6. Next person, they started at 145 and they actually went up to 148. So after minus before would be 148 minus 145, which gives me a difference of 3, et cetera, all the way down like that. All right, so look at what we're interested in. That is the differences, right? The after minus before differences. So I say here that our sample of data is the set of differences, which is just the last line there. So it's -6, +3, -37, 24, -4, 24, -4, -1, -8, +2, and 0. All right, so there is our 9 differences that we have. Okay. I want to make a few observations here before we proceed to do a hypothesis test with this data. In the past, when we've been doing hypothesis tests, I've said, okay, we have a set of data, and here's the sample mean, and here's the sample standard deviation, right? So we started with that. Well, this time I'm actually starting with the actual set of data. I say here, I'm starting with the actual sample of data rather than just the sample mean and sample standard deviation for the sample. And I say I'm just trying to make things a little more realistic. In reality, you collect a bunch of data, that is your sample, and you have to do the computations here. So I figured in this example, let's kind of try to make it as real as possible. And so here's the data set. The original data, of course, was the before and after weights. We made this calculation, and we have our sample of data that we're going to work with, and we're going to have to find the sample mean and the sample standard deviation. So we're going to do calculations that we haven't generally done in hypothesis testing in the past, but usually have to be done because you get the set of data and you work from that. Number 2, we better be sure that we always do the subtraction in the same order for each difference, don't you think? I'm doing after minus before. And I better do that all the way across. If at some point I do before minus after, that's fine if I do it all the way across like that and if I interpret that correctly. But if I do some of it after minus before and some of it before minus after, I have inconsistent data and I have a mess and I can conclude nothing. Finally, I say in number 3 here that we're dealing with a small data set, right? It's only 9. N is equal to 9. So what are we assuming? In the past, when we've done hypothesis testing, the sample has, I think we've always made it bigger than or equal to 30. So we knew with confidence that the central limit theorem, the conclusions applied, and we could conclude if we were looking at a z-score, it was going to be distributed like a z random variable. And if we looked at the t-score, which of course we're going to here, we could have confidence that it was distributed as a t random variable. That's a consequence of the central limit theorem. Here, the sample size is small, and so we might have a problem. But if you recall, it is the case that the central limit theorem holds if the sample size may be small, but we assume that the data come from a normally distributed population to begin with. So if we assume that all these differences come from, if we were to do, put everyone on this diet and get an entire population of differences, it would be normally distributed. If we make that assumption, then a small sample size is fine. When we compute the t-score, we can have confidence that it will be actually distributed like a t-random variable so that we can use the t-charts, right? So I say here, we must be assuming that the differences are normally distributed. That must be what our assumption is here. And we may have strong reason to believe that, or maybe we don't. Often biological phenomena like this are normally distributed, okay? And later on, we will look at ways of analyzing a data set to see whether it looks like probably it came from a normal distribution. But we're not going to do that now, and we're just going to say that, yeah, we're making that assumption that we can go forward with this small data set. And really, I just want to do a small data set so we can do the calculations easily and I don't have to write, huge sets of numbers up here. So we're going to assume that everything is normally distributed and the differences are normally distributed so we can go forward with a small sample. All right, so I have this set of differences. We need to find the sample mean. I'm calling that d bar for the sample mean of differences. And so how do I compute that? Of course, I add them all up. -6 plus 3 minus 37 plus 24 minus 4 minus 1 minus 8 plus 2 plus 0. And I divide by the number there are, which is 9. And I believe I come up with -27 over 9, so I get -3. So the sample mean is 3 pounds, right? It's pounds. I think I will leave the label off just to save room, but we know that it's pounds. Okay, we also need the sample standard deviation to go forward. So we need S sub D bar, right? Which is, pardon me, I guess I'm just doing this, the sample standard deviation first of just the data set. And that is, remember the formula? It's big square root, and I take the first data set, -6, and I subtract the mean, minus -3. Double minus would be make it a positive, right? And then I square that, plus take the next data point, and I subtract the mean, the sample mean, -3, plus, and I keep doing this and doing this and doing this, and the last one, I guess, will be the last data set, 0 minus -3, parentheses, squared, and all of that is under 9 minus 1, right? That's how I get the sample standard deviation for this sample of data. And if you do that, you get 15. You should work this through 15.7876534. It's a lot of digits, but I like to keep all my digits along and then round at the very end, right? That way I trust that I will have accurate results. Okay, look, I got the sample mean right here. I got the sample standard deviation right here. All right, I'm ready to do the hypothesis test now. Now we can kind of start with where we've been starting in the past. Okay, so I say let's test at the 10% significance level. So alpha is equal to 10%. And this guy's getting a little dry. Let me change. Okay, null and alternative hypotheses. I guess I will come right here and see if I can fit all this in. Null and alternative hypotheses. Well, I have to make sure I understand what the quantities are that I'm dealing with. So let me say if mu, how do I word this? If mu is the population mean population mean weight change on the diet, for people on the diet, after 6 months, so I better tell you what my mu means here. Often it's, you know, it's clear, like in maybe the statement of the problem. But here I think we need to make it very clear that we want to look at all these differences and ask ourselves, is the mean of all those differences, if it were for a whole population of the world on the diet, would that mean, you know, what's going on with that mean? So that's what we're looking for. So then what would H naught be? Remember, H naught is the hypothesis, the null hypothesis. Nothing happened. So we are saying that the mean didn't change, right? The diet did nothing. H1, the alternative hypothesis then is we are testing for weight loss, right? So we are hoping that because I did the subtractions in the order of after minus before, well, I want the after. I'm hoping if I'm, you know, trying to push this diet, I hope after is smaller than before. I'm hoping the differences are generally negative. So I'm hoping that the mean is negative. I'm hoping that it's less than 0, right? So this is a left-tailed test. Left-tailed test. I want to just say, look, we could have made it right-tailed, right? We could have made it right? If I had done before minus after, I would have gotten a positive 3 here, correct? Instead of a negative 3. I'd done all the subtractions in the reverse order, and I would have gotten a positive 3. And all that would be saying is here we're saying, hey, it looks like the mean loss was 3 pounds. If I get a positive 3 the other way, I'm saying, well, before and after the mean difference there is a positive 3, which again would mean a loss of 3 pounds. So I could have subtracted it the other way, and I've been doing a right-tailed test, right? Okay, but I pick it one way, and to me the most obvious way is after minus before, and then you see in each case, did I lose weight? Did my difference become negative? Okay. All right, that was number 1. Number 2 says we'll do the graph with the critical value and significance and rejection region and all that. So this is the t random variable, and the degrees of freedom are 9 minus 1, which is 8. All right. If you look that up, most tables will have that. I get a, at alpha equal 10%, right? Or which is 0.1 area in one tail, you get 1.397. And of course it's left-tailed, so it's actually back here at negative 1.397. That's my critical value, right? This is negative t of sub 0.1. And so that means that all this area here, area equals alpha equals 0.1, right? And change my color here. Back here then is all this is the rejection region. You can read that, all this along that line there, right? Okay, 3. says we compute the test statistic and we put it up above in here. So what do we get? The test statistic is the t-score, excuse me, for the sample mean under the assumption that the null hypothesis is true. So I'm kind of running out of room, but I don't think I'm going to write that. I'm just going to say, as we already know, it is the t-score for the sample mean under the assumption that the null hypothesis is true. So how do I get that? I take the actual value minus mu sub 0, and I divide by my standard deviation for the sample, but now I want to divide by the square root of n down there because that's my standard deviation for the mean, right, for the sample mean, right? We have to divide by that square root of n. So when I do this, I get d bar was -3 minus 0 divided by this number, 15.7876534, and it's all divided by the square root of 9, right? And that works out to be about -0.57, all right? And so that's going to go where? About right there, maybe. Not in the rejection region. So step 4, we fail to reject H sub 0. And I guess I'm going to rub this out here to finish up. So step 5, you should, by now you should have paused me and worked this through. Certainly pause me and try to do the final conclusion here, which I will do in a sec. All right, so the final conclusion, maybe I'll try this color, 5. Conclusion. Yes, is that, where am I? At the 10% significance level, we're failing to reject. So there is insufficient evidence to reject, and I'm sorry for the squeaks, to reject, and yeah, you can read that, I think. Yeah, it looks pretty good. Evidence is insufficient evidence to reject H naught, the null hypothesis, which is that, let's see, the claim that there is no mean weight loss. Remember, we are rejecting the null, which is that there is no weight loss. So insufficient evidence to reject the claim that there is no mean weight loss on this diet. All right? So I do not have strong enough evidence to say that there really is, at the 10% significance level, there really is any kind of weight loss on this diet. I think that it is possible. It is the weight loss that we got, this sample mean, is consistent, because there's its t-score. It's consistent with what we would just think of as change that just could be due to randomness, right? So we failed to reject H naught. Okay. So I want to just throw in a few more concepts here. This is pretty easy, right? We're just doing the same sort of thing we've been doing all along. We just had to do it for the differences. But once you had the differences, then everything else goes the same if you can get the mean and standard deviation. Okay. I say here, important concept, statistical significance. All right, note how there is an actual mean weight loss of 3 pounds in the sample, right? There it is, right there. So there may actually be a population mean weight loss associated with the diet, right? It could actually be the case that, yeah, you do lose some amount, right? But our sample mean loss, the -3, turns out to be not large enough for us to conclude that with confidence, right? Its t-score was just not too far out, right? So we can't really conclude that with confidence. What do we say then? We say that this loss here, we say that the loss that we get in the sample is, and you need to fill in, the phrase is, it is not statistically significant. All right? What that means is, I say there, this is another way of saying that the mean of differences is small enough so as to be consistent with it's happening just by chance. Maybe it happened just by chance. So I don't feel I have anything we call statistically significant in this loss. All right, if the sample mean loss had been great enough for its t-score to lie in the rejection region, so if it had turned out to be a more negative number and we'd had a t-score over here in the rejection region, we would reject H naught, and we would believe that there is some evidence for there to be actually a weight loss due to the diet. We would say then that we would have rejected the null, and we would have said that the mean loss was statistically significant, meaning that we believe that the loss is due to more than just random chance, that the diet actually worked. So statistically significant, we usually go with, we've rejected the null. If we don't reject the null, we usually have a result that we say is statistically insignificant. Okay, so break with that, and then what I say below is, there's a lot of writing here, right? But we just have to, this is a little bit of a new idea, or a couple of new ideas we're introducing here, so that's what we have. So we failed to reject the null above, which, as I've said before, doesn't mean we necessarily believe the null to be true. Okay, it isn't necessarily the case that there is no weight loss, mean weight loss. Often when we fail to reject the null so that our result is statistically insignificant, it can simply be because our sample size was too small. A small but actual change in the population mean often cannot be detected with a small sample. A small sample might give us then a change that is just not big enough to be extreme enough to reject the null. So, and I say that is what we sometimes call the curse of a small sample. All right, so let's suppose down below there that we have 100 dieters now. And let's suppose everything else stays the same and that the sample mean stays at -3 pounds and the sample standard deviation is the same as before, 15.787, etc. With n equal to 100, compute the test statistic this time. And you compute it. It's going to turn out to be about -1.9, all right? Excuse me. Now, I need a new table here. I need a new graph here because this is for degrees of freedom equal to 8. I would now need degrees of freedom equal to 99, and that shifts things a little. It's going to shift the t-score a little bit, all right? But if you go back and check, this is in the rejection region. All right, it's a slight, I can almost use this table, use this graph, it'd be a little bit different, but this will still be out far enough to be in the rejection region. So a larger sample can allow us to reach a statistically significant result where a smaller sample may not, all right? And that's just because this n right here, we end up dividing by the square root of a bigger number, and when you work it all out, it'll make this be bigger, more negative. So it throws it out past the critical value. All right, so I say often when reading a study or some other research, you may read that the phrase will come up that results are inconclusive, which usually means that the result was not statistically significant. The researchers failed to reject the null. And you think about it, when often when you're testing something, you're hoping that you can reject the null. You're hoping the diet works, right? So you want to be able to reject the null. So if it turns out that you fail to reject the null, if your result is statistically insignificant, you might word it, or people often word it as, well, the results were inconclusive, right? Which is another way I say here of saying that they might say, well, then we need to do more testing, right? We need to have a bigger sample size maybe. So they're saying we need more money to collect and analyze a larger sample, right? Further testing may lead to a statistically significant result, as in this case, which is usually what researchers want to be able to publish. So if you do a small sample and maybe you get a difference here, but it's not statistically significant, that does suggest, hey, if we could do some more work, get a bigger sample and do this again, we might find a result that it is statistically significant, right? It might not be. If you had a sample of size 100, maybe the difference come out to be so tiny here that the sample mean of the difference would be so tiny that it still would be the case that you'd fail to reject the null. But, in the example I constructed here, it turned out that was enough to bump us over. Okay, so I just want to end with one little observation here. Finally, notice that with our 100-point data sample, though we achieved a statistically significant result, it looks like what? It looks like we can say, hey, it really does look like this diet does cause a change in weight, right? The mean of all the differences turned out to be statistically significant, so that it looks like there really is some change in weight. But so what do I say there? I say notice that with our 100-point data point sample, though we achieved a statistically significant result, I say it doesn't seem to be very significant in a practical sense. Exclamation point. Right? The change, though statistically significant, is rather small, or appears to be small, I should say. Change appears large enough that we have statistical significance, but too small maybe to care about. Okay, so there's evidence here that the diet works, but the evidence is that it doesn't really work very well. Okay, so there is a difference. What I'm pointing out is there's a difference between the notion of statistical significance, did we get a result that indicates something really happened, and practical significance. When you're all done, is it a difference that you really care about? And it looks like probably not if the difference is a mean difference of 3 pounds over 6 months. Now, we'll study this idea in a little more detail when we look at something called confidence intervals, which is another kind of inferential statistics, where we actually come up with ways to estimate with a lot of accuracy or with a lot of confidence the actual change, in this case, in weight. And so I'm getting a little bit ahead here by bringing this up, but I did want to bring it up because I wanted to contrast this with statistical significance. I want to contrast that with the idea that, you ought to back up and look and just ask yourself, is it really something I care about? Is it really significant in the practical sense? And it could be significant one way, but not the other. All right, we'll stop.